Well, it is the 20th of September 2019. It is almost exactly 1 week since my previous Jupiter footage, as in this is Friday night, that was Friday night. The sky was a little darker last time I was filming this, so I guess it was slightly later at night than this, but this is pretty close. Time of recording is probably attached to the YouTube video if you know how to look for that. On the previous one and on this one, I may even remember to put both times in the description. Of course, the time on my camera could be wrong, but it should give you an idea of how many minutes it's been since the previous video of this started. And I haven't checked the website properly for which one's where. I'm assuming Callisto is still way out to the right, with Ganymede a lesser distance out to the right. The website I did check said that Europa should be in the dark at the moment, hidden in Jupiter's shadow, but coming out of Jupiter's shadow sometime after Jupiter disappears from view below the horizon, as seen from here. So I don't know, maybe somebody in Ireland can get you video of that. I can't, because I'm in the wrong place. Someone in Iceland might. But you won't be able to see it from East Coast USA or Canada because it'll still be sunlight there when that happens. So last time I was looking to see which moon was where, the website had plus and minus 10-minute buttons, and there was visible movement on Io on there. So while it's really difficult to be sure on this screen, I can just see one tiny little speck to the right of Jupiter on this screen. You might be seeing Io somewhere closer to Jupiter than Ganymede is, going round and round. And sticking to Newtonian physics, inward acceleration of an object travelling in a circle, treating their orbits as circles, is the square of the linear velocity divided by the radius of the orbit, which is equal to the square of the angular velocity multiplied by the radius of the orbit. And still sticking to Newtonian physics, the inward acceleration due to the planet's gravity, gas giant's gravity in this case, will be its GM divided by the square of the radius of the orbit. So the square of the angular velocity divided by the radius should be proportional to one over the square of the radius. Multiply both sides by the radius. Right, square of the velocity times the radius, proportional to 1 over the square of the radius. Divide both sides by the radius. We get that the square of the angular velocity is inversely proportional to the cube of the radius. Of course, the orbital period, the time it takes for it to go once around, is inversely proportional to the angular velocity, so should be proportional to the square root of the cube of the radius. So if you were to watch this for long enough, or on enough nights, or both, this gets more complicated than that. Because of course Jupiter isn't always at the same distance from us, you'd actually have to do it as a multiple of the angular size of Jupiter rather than just as its position on the screen. But assuming you get a good enough telescope to be able to do that, you should be able to calculate the radius of each moon's orbit as a multiple of Jupiter's diameter, which is a perfectly good unit of measurement in this case, and for observation calculate the time of its orbit, assuming that Jupiter's far enough away for furthest right and furthest left to be opposite sides of the orbit, or even just, you know, furthest right to furthest right, assuming the distance to Jupiter doesn't change too much night to night, or week to week, or however long it takes Callisto to go around. Or if you've got a really good telescope, wait until the moon is actually lined up on the centre of Jupiter. That still doesn't give you the exact orbital period, because of course we're orbiting the Sun and so is Jupiter. You'd actually have to oh Jesus. You'd have to move into the desert and observe Jupiter every night continuously and count how many times, and note at what times each moon crosses between you and Jupiter, until Jupiter is lined up with the same star around the celestial equator, which is massively more of a pain in the arse than watching 10 minutes of this video. But anyway, if you could do that, you ought to be able to figure out the orbital period of each moon around Jupiter as an actual orbital period, and the radii of their orbits in arbitrary units, Jupiter's, or arc seconds if you've got the kit for that, and use those numbers to test the hypothesis that the orbital period will be proportional to the square root of the cube of the orbital radius. But don't feel you have to on my behalf. If I'm going to keep filming stuff like this, probably I should splash out for a camera. No, a camera? I've got a camera. I'm using a camera. A telescope with a camera mount. And a camera compatible with that camera mount, so yeah, another camera. Well, it cost me 2 months' food. People driving motorcycles. Quite disturbing. Can't really be any need. Yeah, 20 minutes is enough, right?